Welcome back, Calculus. We're going to start higher order derivatives. This is going to be a short, sweet section. The objective is to compute higher order derivatives, whatever that means, and determine the meaning of higher order derivatives in context. That will come more throughout the year, but we'll talk briefly about the context of it. Right now, we're going to focus on the mechanics. So if I asked you, what does the derivative of the position function give you? So suppose we had a position function. I'm going to just use h of t, and I'm just going to write the general form of it because the Smurf packet's so fresh in our minds. If I took the derivative of the position function, that would give me the velocity. So how does distance change over time? Distance over time is like miles per hour. That's velocity. Oh, I almost forgot. So the velocity function would be, what is it? Negative gt squared plus initial v. The next question, though, is what does the derivative of this give you? So, kind of like the main question here is, what if we differentiate again? What about the derivative of the derivative? And just think about it, the derivative of velocity. So how does velocity change over time? So what do we call it when our velocity increases or decreases? That's actually what we call acceleration. So the acceleration is the derivative of velocity, and the derivative would just be, what is it, negative? That would just be, there's no t there because the 2 times 2 cancels out, but that becomes 1. Okay, so it would just be, derivative here would just be negative g. And this g is what we call acceleration due to gravity. So that number is not random, that actually checks out. So the idea is what we just found here is that if I take the derivative of the height function twice, also known as the second derivative, we get the acceleration. Moreover, you need to cut this down. More generally, given any function f of x, the derivative lets you find the rate of change. You can copy this down in your notes, which also we call the slope. In case I didn't tell you this before, the derivative is the slope, which is also known as the rate of change. So given a function f of x, the derivative tells us the rate of change, and the derivative of that function, which is what we're going to call the second derivative, tells us the rate of change of the rate of change. Which seems like, what's the point of that? And the best example I can come up with is just acceleration is the rate of change of the rate of change. Distance over time is the rate of change of position, and the rate of change of distance over time is acceleration. We'll talk about this more certainly later in chapter 4, but just kind of like look at this function for a hot second. Actually, I want to draw it a little differently. Okay. So right here, the rate of change is positive, so the function's increasing, but as you can see, it's increasing at an increasing rate. So right kind of in this whole area here, it's increasing at an increasing rate. So the second derivative can kind of give us information about that. Here the function's increasing still, but at a decreasing rate. It's increasing, but slower and slower and slower until it's not increasing anymore. So the function's increasing in both cases, but in the beginning here in orange, it's at an increasing rate. Here it's increasing at a decreasing rate. Here the function's decreasing at a decreasing rate, because decreasing more and more and more. And then here the function's still decreasing, but not quite as much as it was before. It's decreasing at what we call an increasing rate. If that's confusing, we're gonna talk about that more later throughout the year. But anyways, it's a little bit of stuff that the derivative tells us. Okay, so to find the second derivative, what I'm going to call the second derivative is f prime prime. So to find the second derivative, we first find the first derivative, which is green, which is just 3x squared plus 8x plus 1. And pause the video. Sorry, I didn't tell you to do that, but pause it to jot that down. To find the second derivative, we take the derivative of the first derivative, which is just 6x plus 8. So that's how you find the second derivative. Piece of cake. Take a second to copy down these notations. We've already copied down the first derivative notations. So this is what I call the first derivative. That's what we call the second derivative. The third derivative, after 3 tick marks, we just put the number of like the fifth derivative, sixth derivative, seventh derivative, eighth derivative, we just put in parentheses. The parentheses is important because without the parentheses, it's a completely different notation. So another way, if I said the derivative of the function with respect to x, the second derivative can be written like that. The third derivative, the nth derivative. Just like f prime, y prime, y prime prime, y triple prime, y to the, well, I'd be careful writing it like that because that looks like y times y times y times y. So maybe we just don't do that. All right. Nt y dx, the second derivative of y with respect to x, the third derivative of y with respect to x, the nth derivative of y with respect to x. Okay. Find the second derivative of the function. Start off by finding the first derivative. So again, take a minute to copy it down. The derivative of this function is going to be, let's see, 3/2 x to the 1/2 minus 1 is negative 1/2. The derivative of this piece here is going to be negative 12 x to the negative 3. To find the second derivative, piece of cake. Just find the derivative of the derivative. So that's going to be, let's see, negative 1/2 times 3. That's going to be negative 3/4. X to the negative 1/2 minus 1 is negative 3/2. The derivative of this piece, negative 3 times negative 12 is going to be a positive 36 x to the negative 4th. You could do some simplifying, but we're going to leave it like that. Okay. You can rewrite it as negative 3 over 4x to the positive 3/2 plus 36 over x to the positive 4 if you want to add positive exponents. But what I circled is fine. I would not ask you to do more than that. The second derivative of sine of x. All right. So the first derivative of sine of x is going to be, so let me use the same notation. The derivative of sine of x is cosine of x. And if I take the second derivative, which is the derivative of cosine, the derivative of cosine is negative sine. Done. People say this kind of feels like doing powers of I, kind of like I squared, I cubed, I to the fourth, I to the fifth, I to the sixth, and it kind of keeps floating between I, negative I1, negative 1, I, negative I1, negative 1. Sounds similar to that. But anyways, that's the second derivative. Find the second derivative of tangent. Ooh, a little spin here. I'm just going to call, let y be tangent of x so that I don't have to do the notation. Ooh. That blue. So then the derivative of tangent, I believe we said is secant squared. So if I want the second derivative, ooh, we got to be clever here. There's another way to take the derivative of this that we're going to do later, but for now, if I had to differentiate this, I would rewrite it as secant x times secant x. And then use the product rule. So remember the product rule. First function times the derivative of the second plus the derivative of the first function times the second. So let's do that. All right. So the derivative of tangent is secant squared. So the first function, so like this is, look at that is f, and g is the second function. So they're really both the same thing because they're both secant. All right. Anyway, so let's use the product rule. So it's the first function times the derivative of second. The derivative of secant is secant tangent. So I got to do plus the derivative of the first function. The derivative of the first function, which is secant, is still secant tangent. times the second function, which is still secant. Okay. So that's going to be secant squared x tangent x plus secant squared x tangent x. And these are like terms, so there's just 2 secant squared x tangent x. So that is my second derivative. Good. So I just had to use the product rule and write it as a product. There's actually going to be the chain rule is the last rule that we're going to go over. That's going to be another way of getting that answer. Okay. Given y again, let's find the second derivative. So first find the first derivative. The derivative, again, I have to use the product rule again. Fg prime plus f prime g. So it's going to be first function times the derivative of the second. The derivative e of the x is e of the x. Plus. Now I got to take the derivative of the first function. The derivative of x squared is 2x. Times the second function. The second function is e to the x. Okay. I guess I didn't need that dot there because it's implied. So now let's take the second derivative. The second derivative function. So right here I'm going to have a product rule, and right here I'm going to have a secondary product rule. So first for this piece right here, I need to take the derivative of x squared e to the x, which is a product rule, so we're going to need to use this again. But it's exactly the same x squared e to the x here, so this derivative is going to be the whole thing. We're going to have x squared e to the x plus 2x e to the x. And then just bring down that last piece here. It's still there. We do a product rule there. So the first function is 2x times the derivative of e to the x, which is e to the x. Plus, take the derivative of the first function, the derivative of 2x is 2, and then leave e to the x alone. And that's the second derivative. We just got to see if there's any like terms. Looks like these are like terms. So we have x squared e to the x plus 4x e to the x plus 2 e to the x. You can factor in e to the x out if you want. It doesn't matter. And that gives us the second derivative. Leaving like that's fine. That's fine too. And I think this is the last one. So find the fourth derivative, and you guys could probably do this one on your own at this point. So find the first derivative, then we'll find the second, third, fourth derivative, and be done. So the first derivative, 15x to the fourth minus 33x squared plus 8x minus 8. The second derivative is going to be 4 times 15 is 60x to the third minus 66x plus 8. And now let's find the third derivative. 6 times 3 is 180. 180x squared minus 66. And last but not least, let's find the, well, I'm just going to write it like that. The fourth derivative is going to be the derivative of that, which is going to be 180. 180 is 360x. Conceptually, maybe it might make a little bit of sense that the second derivative is acceleration if you're talking about height. What on earth would the third and fourth derivative be? Is there any use for it? We can talk about it later. I've never seen a use for the fourth derivative, except when you get into like sine and stuff, it might come up. But the third derivative, like the derivative of acceleration, I heard it's called the jerk function. And what I would compare that to is like when you're going on a roller coaster and like not only you're accelerating, but like there's a lot of shaking, wobbling. I've heard that has to do with that. Anyways, thanks for watching.